So we're going to quickly finish through these slides on magnetism before we get through induction. So we ended with the magnetic field being a centripetal force because it doesn't really speed up or slow down any charges, any moving charges. It only changes their direction. And that allowed us to think about this making a big circular path. And it turns out that with a little bit of math, right, any sort of force that causes a circular path is a centripetal force. With a little bit of math, we can rearrange things, and depending on the radius of that circle, we are able to, for example, solve for the mass of the moving charge. And so this is a part of the journey that it took to initially find out what's the mass of an electron or what's the charge of an electron. We put these things together and figured out what the mass is. It's not so straightforward. There's a little bit more that had to happen, but this was one of the key experiments. All right, so let's go on to a little bit more practical, like what do these charges or what do these magnetic fields really do? Like, yes, they move the charges around, but charges that are moving really fast aren't very common uh, in most applications, right? Like, yes, charges come from space or the sun, and the magnetic field deflects them, but what is actually more common and more part of our everyday life is actually to think of a current, right? So a moving charge feels a magnetic force due to Fb equaling qvb sine theta. So any any charge that has a velocity v in a magnetic field B feels this magnetic force. Well, guess what? Inside of a wire, there can be moving charges. This is what we call a current. If there's a current inside of a wire, then it's going to feel a magnetic force. Okay, currents are moving charges. Right, like if we have an upwards current through this cylinder, supposed to represent like an infinite wire here. If we have some charges moving through this cylinder here, if well, if we have an upwards current in real life, that means the electrons are moving downwards. Well, then you can think what happens to it in the presence of a magnetic field. And so that's this magnetic field here. The dot is like the arrow tip. So this is a magnetic field pointing out of the page. And you can use your right hand rule. Put your thumb in the direction of the velocity. Okay, so you can point downwards since that's the direction the electrons are moving. And then put your your index finger in the direction of the magnetic field. And so that would be pointing towards yourself. So the velocity is downwards. Magnetic field is, and we might be using different colors than before, is out of the page. And so that leaves the force to be leftwards. Actually, if you, your middle finger should be pointing to the left. That is if you're using your right hand. These are negative charges, however. So this is a negative charge. So the actual force is going to be not to the left, but to the right. You can use your left hand instead, or use your right hand and then flip the answer. But if you use your left hand, your thumb is going to point down, your middle index finger, your pointer finger is going to point towards you, and your middle finger, your force, is going to point to the right. Very bad finger. So currents will feel this magnetic force, and we can compute by the strength that they feel this magnetic force using this equation. I'm not really going to derive this equation, but we'll sort of look at the units and just motivate give you some evidence that it could be true. Now, this is the magnetic force equation, qvb sine theta. Let's look at the units. Q is a coulomb, that's a charge. V is a velocity, which is a meters per second, and B is a magnetic field, which is a Tesla. Okay? In a wire, we're going to have a current, and a current is a coulomb per second, right? So current I is, it's got units of amps, and an amps is equal to a coulomb per second. How much charge over time is going through a piece of a circuit. Now, if we use this equation down here, so once again, I'm not really going to derive it, we're just going to look at the units. that amp is in coulombs per second. L could be the length of the wire, and that's in units of meters. And then we still have this B sine theta part, which is going to be in Teslas. And so the QVB sine theta version on the left, the units match up. We've just sort of moved the seconds around. Instead of being under the velocity for meter per second, we moved it under the coulombs for coulombs per second. And so the force on a wire equation is ILB sine theta, and the units match up with this force equation, the original one we had for a single moving charge. Yeah, so the force on a wire is dependent on its length and the current going through the wire. If you run the electrons really fast, that's going to increase the strength of the wire. The strength of the force on the wire. Or if you increase the size of the wire, then essentially you're just going to have more moving charges on that wire to experience a magnetic force. Let's imagine like a little circuit in which it's just one piece of rectangle. It's like one little rectangle right here, and it's going to feel a magnetic force because we're going to allow a current to go through, and it's going to be inside of a magnetic field. So if I have a magnetic field that's pointing to the right, and this current is in the page, or it's like sitting on top of the page here, let's think about each piece of the current, what's going to happen. So we have these sort of four parts, the top, right, left, and bottom of this rectangle. And we can immediately see that the current, okay, and I'm going to draw this in blue here, the current going, say, through the top, right? So the current will go that way, goes out of the positive end. If this is the current, it's aligned with the magnetic field, and that means that theta equals 0, which is going to imply that our magnetic force is 0 because it has that sine theta term, and sine of 0 is 0. And so the top part of the wire is not going to feel a magnetic force. For the same exact reason actually, the bottom part is also not going to feel a force. It's completely misaligned with the magnetic field. It is to the left, and the magnetic field is to the right. That means theta equals 180 degrees. Sine of 180 degrees is also 0. On the right, though, we have this downwards magnetic field. And now we can use our right-hand rule. Think of the current as being moving positive charge. And so I'm going to draw this separately down here. We have a downwards velocity. The magnetic field is to the right. VB, you should find, and this one can twist your arm a little bit, that the force is pointing right towards you. And so the force will be out of the page. We can do the same analysis over on the left side, but you really kind of don't need to. You can already conclude we're flipping one of these arrows. We're going to have to flip the other one. But anyways, if you have an upwards velocity and a rightwards magnetic field, so this is my velocity and this is my, I didn't label it over here, B, and this is my B. Once again, put your thumb in the direction of the velocity, that's up. Put your magnetic field, your second finger aligned with the magnetic field that's to the right. You're going to get a force that's into the page, and we'll signify that with a cross and a circle. And so on the right side of the wire, it experiences a force out of the page, and on the left side of the wire circuit, it experiences a force into the page. It's actually going to get twisted. That loop of that piece of circuit is going to get twisted, sort of in a clockwise motion when viewed from above. There's numbers here. We can put this onto a homework and do this as a homework exercise and figure out what the sort of net force or net torque on this thing is. Okay, so currents feel magnetic fields Well, it turns out that they also create magnetic fields, okay? So just like in terms of electricity, charges feel electric forces, but they also are the source of electric fields. Well, moving charges feel magnetic forces, and they are also the source of a magnetic field. So this is going to introduce our right-hand rule number two as to how does a current or a moving charge create a magnetic field. And it does so in this way where, now this is on the second right-hand rule, put your thumb in the direction of the moving charge, your fingers, and close your fingers out like you're doing a thumbs up. Your fingers are now wrapping around your thumb in a way that the magnetic field will create. So if your current is upwards, the magnetic field wraps around like this. And so any current is simply creating a magnetic field. Every current we've used so far has a magnetic field that came about from it. And we can quantify this. So it's not just qualitative, it's also quantitative. We have an equation for how strong that magnetic field is. And so for these pictures at the top, we are seeing what the magnetic field looks like if you're sort of sitting it on the page here. So I'll draw in red. I know I keep switching colors here. Maybe I should stick to one scheme. But here, red is this circle indicating, or this dot, I mean, indicating that there's a current coming out of the page. So imagine that picture on the right, this one right here, is now coming out of the page. You can put your thumb towards you, and you see that your fingers will wrap around like this. Okay, they'll wrap around counterclockwise if you're looking at your thumb. On the other hand, if you have a current moving away from you, so that's this X, that means that the current is moving away from you, then the magnetic field, if you point your thumb away, the magnetic field is going to move in a clockwise motion from your point of view. Clockwise motion from your perspective. If you lay a wire on its side and put your thumb to the right, you'll see that, yes, it's a three-dimensional sort of field that goes around and wraps around this wire like this. But if you are looking at the magnetic field just sitting on the page, at the point that it intersects the page, it's coming out of the page, above the wire, and into the page below the wire like this. And so that's what this third picture is supposed to represent. And it turns out, and this kind of makes sense, that the further you get from the wire, the weaker that magnetic field is. And it follows this relationship, B equals mu naught I over 2 pi r. This is for an infinitely long wire, which doesn't exist, but it's a good enough approximation for it to be a useful equation. Mu naught is a constant. It's actually 4 pi times 10 to the minus 7 Tesla meters per amps. Very strange unit, but you may also have seen it, I think, as 1.256 or so times 10 to the minus 6 Tesla meters per amp. That's just somebody doing 4 times pi, and that's what it equals. So same number. And r is the distance from the wire. Like if you're interested in the point here, let's call this point P, and you're like, what is the magnetic field at point P? Well, you need this distance that goes directly from the wire that has the current directly to that point P. And so that's going to be r, which you plug into the equation. And so let's just look at these right-hand rules so far. Okay, we have this first one which we learned, the very bad finger one, where V is representing the velocity, B is representing the magnetic field, and F is representing the force. And this follows the equation F equals QVB sine theta. You just do have to remember that you flip your answer if you're using a negative sign, or you use your left hand instead. Both are identical ways to solve a problem with a negative sign, negative charge. Okay, so this is for the interplay between force, magnetic field, and the velocity of a particle, of a charged particle. This right-hand rule number two is about the magnetic field generated by a current. Okay, so these are two different things, right? There's no force involved in this right-hand rule number two. And in this one, well, current is kind of like positive charge velocity anyways. You can think of it either way. But if the current goes up, then this magnetic field wraps around in this way as pictured. And so this one's a little bit less, a little bit easier to think about it and uh, not as easy to mess up as the other one. Uh, you can, I don't know if there's a sort of negative thing to worry about. It's not very common that we talk about the current of electrons, but you could, I guess, think about it that way and use the left hand rule. But I would say let's stick to the right hand rule when it comes to right hand rule number two. So we have a few examples, and I have full solutions, which you can click on these links and head over on to the right page on the YouTube channel and find a full solution to a problem like this. This is one in which we have a wire. You can't see it. It's going out of the page, and it's at the center of the screen here. And that wire, so it's right here, it's coming out of the page. That wire is going to create a magnetic field, and a moving charge is going to feel, this charge is going to feel that magnetic field, and therefore a magnetic force. And so it's going to combine both these concepts together. Uh, we also, one more thing about magnetic fields is that they, just like electric fields, they follow superposition. They can be superimposed. And so what that means is if you have multiple sources of a magnetic field, then you can add the magnetic field to create like a net magnetic field in a vector addition. This can be very complicated. This can be complex, and we can take this to a very difficult place, but we'll try not to take it to such a sort of mathematical nightmare type of scenario. But if you recall, this is like when I said that if I have a positive charge and it makes a field, an electric field, so this is not magnetic field anymore, that sort of goes out like that. And if you have a negative charge, so let me just draw a few arrows. If you have a negative charge, let's draw that in red. Or sorry, it doesn't need to be negative. Let's do a positive charge over here, and it has its own electric field, which does this kind of a thing. The electric field just sort of comes out and is emitted by this positive charge. There is a net electric field, which you can add them together. For example, in this region, there's going to be equal amounts of down right and up left field. You're going to find that exactly in the middle, if these charges are equal, they're going to have no electric field. And at this point where you have this combination of up and right, well, the net field is going to be up and to the right. And so that's the concept of superposition, is just multiple vectors can add up together in a sort of independent way. But mathematically, it can be challenging. This problem, there's a problem here. We will sort of think about it in as simple as this kind of problem can be, which I still think is actually a little bit complicated. We're going to have, and again, there's a full solution up on YouTube, which you can look at, but we're going to have, and I'm going to draw this in red, an upwards current, right? It's going to generate a magnetic field. It's going to generate a magnetic field like this, which goes around. And then you have a horizontal current, which I'll do in blue, horizontal current. It's going to generate its own magnetic field, which goes around like this. And we're going to see how do they connect together at these specific points P and Q. And so look through that problem for specifics. All right, well, one more important, very important geometry to consider, and you'll see this in the next set of slides actually, and that is the loop, a loop of wire. Like what happens there, okay? And so I have a little sketch of that on the left here of what a sort of just one little loop of wire and the magnetic field following that loop of wire in blue. And so if you do this, if you just sort of, I would recommend that you do this, put your thumb as it follows the current I, and let me make sure I'm getting this right. And so we'll say that this is going to end up going that way. So start from here and put your thumb to the right and hold a sort of thumbs up pose on your hand as you follow this little like sort of fair ride loop-de-loop roller coaster, and you'll find that your fingers have this pattern which follows these blue curls over here. And what you find is that inside of the circle that you make during this loop-de-loop, the magnetic field is always pointing towards you, always pointing towards you. Everywhere in here, it's pointing towards you. And conversely, everywhere outside this loop-de-loop, it's pointing away from you. And so that's what this second picture is supposed to represent, that the magnetic field is always sort of pointing towards you inside and always away on the outside. And a single loop of wire, what we'll find, it kind of behaves like a magnet, okay? If you sort of put a loop of wire on its side like this, well, let me do this in red actually, since that's the color we use for the current. Uh, yeah, well, actually, we can see some here. But anyways, if you have a loop of wire like this, it's going to form a magnetic field which points up inside, a lot like a north and a south end of a magnet. Here are many examples where loops are important, and in fact, we tend to combine lots of loops of wires, or in a big spiral. We call that thing a solenoid. Very useful object uh, in which we have multiple loops of wire, well, really one spiral of wire, and the current goes through, creating this magnetic field. We can get much more powerful magnets using this by using a current than we can with permanent magnets like the iron bar magnets. You know, those things are called permanent magnets because they don't need any sort of current or charge flowing. They have, you know, quantum mechanics that makes them work. But the one that's involved with currents, those, because we can create very high currents, we can create very powerful magnets, such as, you know, one strong enough to lift a car, or one which creates a magnetic field which is stronger than the sun. In an MRI, this is about on the order of 1 Tesla, which is a huge magnetic field. Uh, we can only do that with currents, and so the challenge there is how do we make a current that goes incredibly fast without sort of damaging everything along the way. We have ways to do that, but yeah, so solenoids, very important device. One more right-hand rule. It's the same as right-hand rule number 2, but specifically with solenoids, there's a different way you can think about this. Um, the currents can go in a big spiral, and depending on what direction they go, so it can be sort of a clockwise or counterclockwise when looked from above. But you can, if you follow your fingers, your 4 fingers in the direction of the current, then the thumb will be the magnetic field generated by that current inside of the loops. Okay, and I would focus on that middle picture. That if your currents are going, say, counterclockwise when viewed from above, then the magnetic field will go upwards as pictured. If your current was to reverse direction suddenly and the current was going that way instead, then the magnetic field would be going downwards inside. And so you can get there by using right-hand rule number 2. But in this case, we've sort of swapped fingers. This is now I, and this is now B. All right, so uh, hopefully we learned a lot here about the magnetic field Mainly what I want you to have taken away is that you can discern which way a magnet attracts and repels based on the north and south end. You can relate the like how electric charges feel about magnetic fields, really due to that FB equals QVB sine theta and all of the sort of following equations that came from that. And also that moving charges create a magnetic field in this mu naught I over 2 pi r sort of way, and that we can compute that as well. So these are the big players, F equals QVB sine theta, and B equals mu naught I over 2 pi r. There were a few others, but they were consequences of these two equations, mostly the top one. All right, I'll see you in the induction slides pretty soon here.